Well, how's everybody doing out there? Well, welcome to day 8 of Corona Online School. So, we're actually finishing up chapter 9. So, this will actually be the last of this unit. And so, this unit's talking a lot about three dimensional stuff. So, we'll get into a lot more detail later when we do these. So, this is kind of just a brief introduction. So, there's a lot of definitions and things like that. So, I won't bore you kind of talking through a lot of this stuff, but I'll let you do a lot of this stuff on your own, but you can ask me questions if you have any. So we're going to start off by looking at just a cube to begin with. So it's kind of the simplest of our three-dimensional objects. And this is true of all dimensional objects. So what we're going to do is we're going to notice that all of these polyhedra that we're going to talk about have faces, they have edges, they have vertices, and then I'm going to talk a little bit about what's called a net. So if we look, the faces are all the blue colored shapes on our cube. So all the flat sides of our cube are going to be the faces. And if we count them up, since this is like the same thing as a six-sided die, we know that there are six faces on a cube. And the edges are going to be the lines where the two faces actually meet. And so if we were to count all these guys up, and remember there's ones we can't see, but there's going to be four edges across the top. Then there's going to be another four along the bottom. We just can't see two of them, so we're going to have four down here. And then we've got four that go up and down around the side of the cube. So it turns out that there's 4 times 3, or 12, edges on our cube. And then a vertex is where all the different edges meet. And so again, they're highlighted in blue for you. And so again, if we count them, there's 4 on the top, and there'll be 4 on the bottom. So there's going to be 8 vertices total on our cube. So kind of keep this in mind. This is going to be a number that we're going to try to do something with here in a little bit. So the last thing on this is there's what's called a net. And so a net is a two-dimensional shape that allows you to basically fold it and cut it and tape it together and turn it into a nice three-dimensional shape. And so if we look, the picture on the left here is actually the shape of would form into a cube. So if you were to fold this along the lines and then take these two sides and kind of bend them up, you can almost, and this would kind of come this way and just wrap over itself. You can almost see how you could actually fold this guy into a cube. And so I'm going to have some stuff in the packet so that way you guys can print some stuff out if you have a printer and try to fold some stuff on your own. Like we would do this all in class, of course, if we were in class, but we're not in class, so we'll have to make the best of it. All right. So what we want to do is use these shapes to actually develop what's called Euler's formula. So again, I'm going to include some nets in the packet so that way you guys can work through these, cut them out if you have them available. If you don't, you can go online at least and or at least you can look at them and count them without actually necessarily folding them. If you don't have to, it's just more fun if you can fold them. And so we want to name what the solids are called in the table, count the total number of faces, vertices, and edges, and then record the results down here. And then we're going to look for a pattern. So I'll go ahead and, since we did the cube already, I'll go ahead and write this one in. So we saw that there were 6 faces to our cube. There were 8 vertices, and there were 12 edges. And so I'll let you fill the rest of it out. And then again, like with some of the other shapes I send you, feel free to fill that chart out too. And then hopefully from there, you'll come up with what's called Euler's formula. So I'm going to leave it as a surprise here. I'm not going to give it away, at least right now. So if you have trouble with it or something like that, let me know. But I'm hoping you can figure it out. And then once you figure out Euler's formula, then you can work on practice 1 here. So this gives you a couple different scenarios for vertices and edges, and you're going to find the faces and stuff. So I'll leave that for you guys. And so now let's talk about some definitions. So all of the shapes that we're talking about in this section are going to be what are called polyhedron. And so a polyhedron is just a three-dimensional solid whose faces are polygons joined at their edges. So remember, so a polygon means it has to be like a triangle, a square, a pentagon, a hexagon, an octagon, anything like that. So circles won't count. So we are going to talk about cylinders and cones. Those won't be polyhedron in this case. So it has to have polygon shapes to be a polyhedron. So every polyhedron contains faces, vertices, and edges, and so we saw that on the cube, and so that'll be true on all these other shapes. And if you have more than one polyhedron, it's called polyhedra. All right, so let's talk about some of the different shapes here. So we'll start off with prisms. So prisms are solid shapes. They come in many shapes and sizes, and then every prism has the following characteristics. So for the base, a prism always has two bases, and they're always going to be exactly the same. So they're going to be two congruent polygons, and then they're going to be connected by parallel lines. So in this case, and so these would be our bases on these guys. So in this case, the triangles are bases. Now the lateral edges, these are the lines that actually connect the bases together. So like on this first one, we've got three lateral edges. So we've got this one, we've got this one, and then we've got the dotted one that's kind of behind there that we can't actually see. So those would be our three lateral edges. And then the lateral faces, so those are going to be typically rectangles or squares that are formed by those lateral edges. So like in this case, like this guy would be a lateral edge. There's one down here, and then there's one kind of on the backside that we can't actually see. So those would be our lateral edges. And so this last part's really, really important. So the way we actually describe a prism is not by the lateral faces or anything. It's always by the bases, because that's what's going to be unique. So, because if you notice, all these guys have rectangles that connect everything up. So what's different about all of these are the bases. And so when we define a base or a prism, it's always by the base. So in this case, the first one, since it's made of triangles on both ends, we would say this is a triangular base. And so this guy, if we count the sides, it's 1, 2, 3, 4, 5, 6, 7, 8. So it's 8-sided. So this would be an octagonal. Not base, what am I doing? Prism, sorry. And the last one would be a square prism, because again, the base is a square. So kind of keep that in mind when you're looking at these, because sometimes people will get confused and they might call it a rectangular prism just because, you know, 4 of the sides are rectangles, when in reality, it's the 2 sides that match that are the ones that actually count, not those other 4 sides or 8 sides and things like that. All right. And so all these are polyhedra because, again, they're all formed by different polygons. So the cylinder, in this case, which we've seen all the time, like cans and stuff like that, are cylinders. So again, just like the prism, they have 2 bases, but in this case, the bases are going to be circles. And again, they're contained in like parallel planes, but these are not polyhedra. Oops, hedra. Because there's no polygons anywhere in this, like even the sides are rounded. So there's no polygons at all formed in making these cylinders. So cylinders are not an example of a polyhedra in this case. All right, so pyramids are similar to a cylinder, but instead, or a prism, but instead of having 2 bases, it's just going to have a single base, and then it meets at a point at the very top, which is actually what's called the apex of the pyramid. So these points where those kind of lateral faces join is what's called the apex. And so again, a pyramid has just one base. The lateral faces are going to be triangles all the time. So in this case, like they're going to be different sizes and different shapes depending on how big the base polygon is. But they're always going to be triangle shaped, and they're always going to intersect at that top point, which would be called the apex. And again, we describe pyramids the same way we would describe prism. So it's again based on the base itself. So in this case, like this would be a square pyramid. And then this one is 1, 2, 3, 4, 5, 6. So this is a six-sided. So this would be a hexagonal pyramid. All right. And so similar to the pyramid is our cone. And so again, if you think back to, an ice cream sugar cone, like that's exactly what we're talking about in this case. And so again, same idea is true. There's going to be a single base, but the base is going to be a circle. And the lateral face is actually formed by taking the sector of a circle. And so if you look over here on the right, I've actually drawn a net for a cone. So this is actually what the net of a cone would look like. So we would roll this up to meet each other, and then we'd fold the circle over, and that would actually give us our cone shape in that case. And so again, there's no polygons involved in this, so this is not a polyhedra either. Oh, I'm having a spelling problem today. Yeah. So the only polyhedra we have are going to be our pyramids and our prisms. Our cylinders and our cones are not going to be polyhedra, so just keep that in mind. And so from here, I'm going to have you do this on your own. So I've got a picture on each side, and your goal is to go through, name what the solid is, what's the base, what's the shape of the lateral face, and is it a polyhedron or not. So I'll let you guys work on that one on your own. And then finally, the last thing we want to talk about are these things called Platonic solids. And so there's two kind of famous solids that are out there. So there's Platonic solids, which are these 5 that we have here. And there's another group that's called the Archimedean solids, there are 13 of those. And so if you get a chance, like you should Google them. They're definitely pretty cool looking. They make some really awesome shapes, and you could talk about the number of faces and edges and stuff like that. And they're really, really big. So the Platonic solids, so obviously there's 5 of them, and we've got a picture kind of each one of them. And I don't know if any of you guys ever played D&D or anything like that, but these are actually the dice from Dungeons and Dragons. Like these are the shapes that they use. So the tetrahedron is actually like a 4-sided die. A cube is a 6-sided die. An octahedron is an 8-sided die. A cosahedron is a 20-sided die, and the dodecahedron is a 12-sided die. So there's actually cool dice for these, so it makes a nice probability problem and things like that, because they're kind of different numbers than just your standard 1 through 6. And so there's obviously 5 of these solids. So I'm going to let you answer most of these, but I do want to talk a little bit about what makes them a Platonic solid. So when they were coming up with these solids, the goal was to use simple shaped polygons and to try to see, how many 3-dimensional shapes you could actually make from these polygons. And so the Platonic solids, the difference between these and the Archimedean solids is Platonic solids, you're only allowed to use one type of polygon. So if you notice, for each one of these, you either have a triangle as a face, a square as a face, or a pentagon. Those are your only choices. Archimedean solids actually allow you to have a mix of both. So you could have triangles with squares with pentagons, and so that's what makes those a little bit different, and that's why there's more of them. So there's actually more Archimedean solids than there are Platonic solids. So that's one of the things that make these a Platonic solid, is they're formed with just one shape. And so the other thing is, and this is kind of a reason they work, is it has to do with how many edges you can, how many triangles you can actually join at an edge and form some kind of a solid from it. And so again, this is kind of unfortunate because I have all these cool magnets that I could show you this. So I'm going to try to draw some of them. I mean, this could be a disaster, but we'll see. So because the goal is you're allowed to have 3 triangles or 3 whatevers at a point. So if we're thinking of this in terms of a net, like the tetrahedron looks kind of like this. Oops, hold on. And so notice what I've got is I've got, oh, let me see, where's the fourth side going to be? Oh, hold on, wait, let me see. Do I have this the right way? I'm trying to not butcher this up. So they're all equilateral triangles. There we go, now I've got it. I drew it the wrong way. So basically, if I take these three equilateral triangles and form them at a point, then remember these are 60, 60, 60 degrees for each one of them, so it makes 180. So I'm able to fold these guys over and turn it into a tetrahedron. So if I fold this over, this will actually give me that shape, and then I would then I would attach those together with one other triangle. So like an octahedron, so we can actually form a couple more of these triangles together. So I'm trying to think. Oh, I hate to butcher this up. Let's see. I think it's those four. 1, 2, 3, 4. Yeah, so if we join these four together, then basically we can fold those guys over, and then that's going to give us our octahedron in this case. And then if we do the icosahedron, we can actually get 5 of these guys together, if I can draw this right. Whew, my art skills are poorly lacking. But anyway, so if I put those 5 triangles together, then I can actually form the icosahedron. You can almost see that on the top. And so the problem is, if I try to go one more, what happens if I try to put 6 of these triangles together? Well, if I put 6 of these triangles together, I basically end up with a flat. So, because if you think about it, each of these angles would be 60. So 6 times 60 would give me 360. So it wouldn't fold. There's no way to bend it up. So 6 triangles, if I put 6 of those together, it's going to give me a 2-dimensional object, not a 3-dimensional object. So that's why there's only 3 triangle shapes that can actually be formed from a Platonic solid. So the tetrahedron has 3 triangles that meet at a point. The octahedron has 4 triangles that meet at a point. The icosahedron has 5 triangles that meet at a point. And if I try to go to 6, it's no longer a 3-dimensional object. So that kind of takes care of all of our triangles. So the same thing would be true for the cube. If I take a cube and I join them together at a single point, if I put 3 of them there and I fold it up, that's going to be half of the cube. And if I do the same thing, that would give me the other half of the cube. And if I add all these degrees up, since they're all 90, that gives me 270 degrees. So that allows me to fold it and turn it into a 3-dimensional shape. But what happens if I try to put 4 cubes together? Well, that adds up to 360 and I get a flat again. So that's why there's only one square Platonic solid, because it needs 3 shapes to get that point. If I go up to 4, it's a flat. It's no longer going to be a 3-dimensional object. And so the same thing's true with the pentagon, but I am definitely not going to try to do that. I mean, that would be a disaster. But theoretically, if you're good enough and skilled enough at art, you can actually take and prove that you can't put any more than 3 faces of a pentagon together at the same time. So 3 pentagons at a point. If you try to go more than 3, it ends up actually overlapping. It doesn't even make a flat. It's just way too big. So again, and if you try to go up to a 6-sided, it doesn't work either. So that's why triangles, squares, and pentagons are your only possibilities for these Platonic solids. So that's what makes them a Platonic solid. I probably went into way more detail than you guys care about, but it's kind of a cool thing how these were actually invented. I mean, and I'm talking a long time ago. I mean, like this is like 200, 300 AD. I mean, this is old stuff. So it's pretty neat. So I'll leave the rest of these for you guys to actually check out. So you should be able to answer them just by looking at the pictures and stuff like that. Otherwise, I'll get the nets to you guys so that way you can cut them out and make some shapes. And then there is going to be an assignment coming up that has you guys making your own some kind of shape. So I'm going to list some criteria and stuff like that, and I'll post it for you guys so that way you'll have something to work on. And I think, if I'm not mistaken, next Wednesday is our first exam, if I'm not mistaken. So if I can, I'll try to get some review stuff together for Monday so that way we can have a review on Monday, and then we'll be ready to take the test on Wednesday. So if anybody has any questions, just let me know, and I'll talk to you later.